All right, we're just going to review some things here for starter. Y'all have that test review? Anybody not have it? You need it? Yeah, test is Monday. Right. All right, so we got the list of stuff here. So, just be sure that you go through that you know Q equals VA, know how to do that you can fill in one of those charts, that you can make a hydraulic grade line, and that you know the basics of head loss theory, and that you can find head loss just using the head loss charts, okay, on page, I think it's 108. Be sure you can calculate minor losses, and that you just know the basics of system analysis, that you equalize the head loss, okay. So those are the main things to be able to do. All right, so here's just some old test questions, and keep in mind, these are kind of examples of what I've done in the past. They're not what I'm going to do on this test for sure. I don't know. I haven't made the thing up yet, so I don't know. Okay. But these are just to kind of help you get, review a little bit. They're not like, if you can do this, you could do the test. It's not quite that simple. Okay, just look at the list. Be sure you can do the stuff on the list. All right. So on that first one, if the pressure goes up, what happens to the head loss? Yeah, pressure doesn't affect it at all. Yeah, not directly. Yeah, right. Velocity does, not pressure though. Rougher pipe, you get, yeah, we would hope higher head loss. Right? Okay. All right. All right, okay. Now this next one here is a Q equals VA kind of thing. When I see this, what I'm going to be thinking about here is I want to get the areas of these things, of these pipes, and I'm going to want to do it in square feet, okay? So the first thing that I'm going to need to do is I'm going to need to get things in feet, is how I'm going to need to set them up. So I've got 15-inch diameter pipe, so the radius then is 7.5 inches. And then the radius is 7.5 inches over 12 feet. So I'll get the radius then. All right, and the radius there is 0.625, and that'll be feet. So the area then will be pi times 0.625 feet squared, and that'll get you the area, okay? So the area of that pipe is 1.23 square feet. And then you can do the same thing over here. The radius is 2.5 inches. So the radius is 2.5 over 12. So that'll get you the radius in feet. Okay. And that's 0.2083. So then you can find the area. Take pi times the radius. Squared. And that'll get you the area, and that's 0.136. Okay. So there's the area. Now, once you get the two areas done, you've done most of it. Okay. So the rest that you need to do is to take the, get the flow rate going through, and that equals the velocity times the area, right? So the velocity then you've given is 1.2 feet per second. And then you've got the area there, and that's 1.23 square feet. So you can get the flow rate, and that's 1.47 cubic feet per second. Okay. And then if you want the velocity out, what you do is you'll take the flow rate going through divided by the area on the outside, so to speak, or the out pipe, you might say. So the velocity out will be that 1.47 cubic feet per second divided by the area on the pipe going out. That's 0.136 square feet. So that'll get you the out velocity. And that is 10.8 feet per second. Okay. Yeah. Sure, yeah. There's a quicker way to do it. Now, all these formulas I just went through, you know, were basically V equals QA is on the formula sheet, of course. You could also just speed this all up if you wanted. And what you do, you take 1.2. So the velocity out here, I guess, if you were to do this other method, is V in times, in this case, you got diameters, so I'd use D out, or no, D in over D out. Let's go back here if we can. So that's D in over D out, D being diameter, squared, okay? Okay, so that's the equation there. So what you do then is you take that V coming in this case, and that's 1.2 feet per second. And then just multiply it by the ratio of the diameter in, which is 15 inches, over the diameter out, which is 5 inches. And then you'd square that. Okay. So that'd be 1.2 feet per second times 15 over 3 is 3. The units go away. You're going to square that. So that's going to be 9. So that'll get you 10.8. So that's the quick way to do it if you remember all this stuff. So any questions on that?
And we always have to convert the inches to feet, right?
Kind of depends which method you're using. If you're doing it this way, yeah, because you want to match the feet per second on the velocity.
Right.
The units you want to match the units. So that's why. Okay. So other questions on it? Okay. Okay. All right. Now this next one here, what you're going to want to do is build a chart out of this thing. Now remember, everything on the chart has to be in feet. So if you want the pressure head, which is what you want, at A, what you do, you take the 50 psi times 2 feet per psi, and that'll get you the pressure head at A, and that's going to be 100 and some odd. That's going to be 115.5, and that's feet, which is what you want. And then while I was doing this, I'd get the head loss. Okay, so what the head loss is, if you go to the chart, what you'll see is the head loss is it's 4.38 feet per 100.
And you look up 4-inch pipe with 200 GPM.
Right. Yeah, 4-inch pipe, 200 gallons per minute, C100. So you can get the head loss. So what you do then, you take that 4.38 feet and multiply it by 9.45, because you got 945 feet. That's 9.45 100-foot lengths. And when you do that, you'll get 41.39 feet.
Wait, did you get the 9.45 from the chart?
No, I'm getting it from the length from A to B.
Oh, okay.
Okay. And I'm converting it into 100-foot lengths, because that's what.
So you converted the head loss figure that you got in the chart, and you're also converting the length. Okay.
Mm-hmm. So once you've done those things, you got what you need to do the stuff with the charts. Okay. We're going to ignore velocity head for a couple of reasons. One thing is it says to, but the other thing is that it looks like the pipe size doesn't change from A to B. If you got a certain flow going through there, you'll have the same velocity in both places, and the velocity head will just cancel out anyway. So we don't need to worry about velocity head on this. Okay. Good with that?
Now, if the C said 140, how would that be different?
If C was 140, what you'd have to do would be to take the 200 gallons per minute and convert it into an equivalent flow that you would then use on the head loss charts. So you take 200, if C was 140, now it isn't, but if it were, mm-hmm. What you do is you would go and first get an equivalent flow. All right. So if C was 140, we've got, what, 200 gallons per minute. What you would do is you'd find Q equivalent. And to find that, you take the 200 gallons per minute, mm-hmm. and multiply it by 100 over 140. And this is the flow that you'd use on the head loss charts.
Okay.
And then you'd go to the head loss charts and use whatever that comes out to be.
Yeah, whatever that comes.
About,
now, like let's say it says 231, and there's like 220 and 240. Mm-hmm. Which one do I pick, the high one or the low one? Like bracket.
Well, it's not that. Don't hang up on that. You know, that's not a huge deal. Okay. Interpolating, what you're doing, you're interpolating off the charts. just make a reasonable guess. I mean, if you got, if you got 200 and 220 on the charts and your flow is 202, I just use 200. That's close enough. You know what I mean?
Whichever one's closer.
Yeah, you could do it that way. Yeah.
Yeah, like if it's 215, you go with 220.
Yeah.
If it's 210,
you could go split them. Add them up and divide by 2. I mean, don't. It's not something I want you to spend an hour on figuring that out. That's that's not the point here. Okay. So in this case, you'd use 142, 143 GPM. Okay.
Right.
When you went to the chart. Okay. All right, now you got everything to do with the chart there, so now you can go ahead and do that. So, you just fill everything in and do all this. We've been doing this quite a lot. So we got elevation, pressure head, velocity head, and then total. And, you got the elevation is 135. You got the pressure head is 115 and change, right? 15.5. We're going to ignore velocity head. We've got A, and then we got the head loss, and then we got B. Okay. So what do we got? We got 250.5. The head loss we just found, and that is 41.39. So if we take 250.5 minus the head loss, because head loss takes energy out of the system, you get 209.11. You got 176 right there. Ignoring that, so you're going to take 209.11, take away 176, and you'll get the energy there is 33.11.
The pressure head, right?
Yeah, now that's feet. Okay, so what you're going to do to find the pressure at B is you're going to take 33.11 feet times 0.433 psi per foot. Okay.
Don't you want it all in feet though?
Well, you want everything in the chart in feet, but the question's asking what's the pressure.
Oh, so you want okay, so you take that number and then got it.
Yeah. So just remember whatever you got on the chart is in feet. So that's 14.3 psi.
Mm-hmm.
Yeah.
Just a question about on the test. If we're within like point something feet of, is that gonna affect how you grade it? Okay. I was on number 4 and I was sticking with Alan, and same even with number 3. I was within like a few decimal points.
All right.
Okay.
That's just,
I just don't know with how far my calculator is going out and rounding. Okay.
And really, I mean, from a practical point of view, saying there's 33.11 feet, it's like,
yeah. No.
You're
as
lucky.
Long as the whole, I guess you can say more or less, the whole number is correct.
Yeah. And I just look at your process too.
Okay.
I'm not too worried about little rounding differences. Yeah, right.
Because I mean, I said I'm within like 0.3 on this one, and then I'm within 0.2 on the second one.
All right.
So it was just like.
Yeah, it's probably fine as long as your process is okay.
Okay.
Don't worry about the rounding so much. Okay. Okay, this one here, we want to find the equivalent length, and this should say half open. There were some copies of the review that said quarter open. Just be sure that yours says half. Okay. So what you're going to do here, there's a few steps here, and just be sure you know the steps. I mean, the first step is to get the L over D value, and that's off the chart. Well, I don't get a lot of charts, I know, but this is off the
Equivalent.
yeah,
What is it called?
L over D chart. Okay. So a half open gate valve has a length to diameter ratio of 180. Okay, half open gate valve. So the first thing you do is you find the L over D, okay? Now that's a ratio, so it doesn't have any units. It's just 180. Now we got 6-inch pipe. So what that is half a foot. Because I want to be in feet to match everything else. So if L over D is 180, if I take L over D, which is 180, and multiply it by the D, which is the pipe diameter, I'll get the equivalent length of that fitting. It's 90 feet. Okay. So you take the L over D times the diameter, and that gets you how many feet of pipe the thing equals as far as creating head loss. So that half open gate valve creates the same head loss as 90 feet of pipe. So I've already got 263 feet before the valve. I got 90 feet for the valve itself half open, and then I've got 104 feet. So if I just add those things together, I'll get the total length of a system of just pure pipe that'll have the same head loss as the system I've got up there. And that comes up to be 457 feet. So that 263 feet of pipe, a half open gate valve, and 104 feet of pipe has the same head loss as 457 feet of just straight pipe. Okay. Now the head loss for 500 gallons per minute, what that is, if you look that up, is 3.32. And that's feet per 100 feet. So I'll take that, 3.32 feet per 100, and I've got 4.57 100-foot lengths. So if I multiply that out, I'll get 15.17 feet of head loss. So that's how much head loss you have in that system.
Now, you could do it as individual sections, right?
Yeah.
Okay, I just want to, that's the way I did it, as each individual section.
Yeah, that's fine.
And then I added the totals up.
Mm-hmm. Yeah, you could do it that way too. There's different ways to
Yeah,
put it together.
Wait, I got it right.
Yeah. Okay. All right, so you get L over D, you got to get the equivalent length, then you got to find the head loss for the equivalent length. So there's 3 steps in there. Okay. And then this last one here, all right, you've got at the top of an open reservoir there, you're in an elevation of 367. So that's the elevation. And that's at the reservoir. There's no pressure head up there. And velocity head will ignore. So what you got there is 367 feet of energy. Then you got the head loss, okay? Now on this one, we're going to have to back into what the head loss is. So the elevation of the hydrant's 241. Now it needs to have 20 psi of pressure there. And we know we got 2.31 feet per psi. So that's 46.2 feet. So that's the pressure head here. And there's no velocity head, we're just ignoring that. So what I got at the hydrant side is I need to keep the water up at 241 feet, plus I need 46.2 feet of head there for pressure. So I need a total of 287.2 at the hydrants. So I can figure out how much head loss I can have by taking 367, which I got at the reservoir, minus what I need at the hydrant. And when I subtract that off, I get 79.8. So that's how much, that's the maximum head loss I can have. I can't have more than that, because if I do, that pressure will start to drop off. Okay. So what I want to do, I want to go to the charts. And what I'll do if I go to the chart is I'll take the 79.8 total feet. And this thing's 3572 long, so 35.72, 100-foot lengths. I'll divide that out, okay? And what I'll get out of that is the head loss per 100 feet. And that comes out to be 2.23. So that's the head loss that I can have per 100 feet of pipe, and still keep enough energy at the hydrant to keep my pressure up where it needs to be. Okay. You all right with that? So what I'm going to do, I'm going to notice, okay, I got C100 and I need 3,000 gallons per minute. So I'm going to look at the different pipe sizes and see what sort of head loss they got. So I looked at 10, 12, and 14. So what I've got there is 7.61, 3.13, or yeah, 3.13, and 1.48. So those are my different head losses for each of those three pipe sizes. Now, the deal on this is that is as much head loss as I can have. I can't have more. Because if I do, my pressure will drop too low. Yeah, 12-inch won't work. That's too much head loss, so I'm going to have to go with 14-inch on that. What's that? Yeah, on this one, the 2.23 is as high as it can go. So I want to stay below 2.23. So it's the first pipe that's below. That's what I'll use. So that'll be 14-inch pipe. Okay. Yeah, when it's out, just go way, way high. That's what I put in my house, 24-inch. Good pressure at my sink. It takes a week to get the water down there. Yeah. Right, so we get on that. That hits most of the key ideas for this stuff. Okay, Q equals VA, and chart. Put together a chart to find energy and all that, and then finding head loss, minor losses. No, I'll have all the stuff you need, all the formula sheets you need. So I'll get you a head loss chart and a minor loss chart. And that's pretty much about it, I think. Yeah.
We're getting the sizes for the minor.
Oh yeah, minor loss chart. Yeah, the L over D. Yeah.
What page is the minor head loss chart?
123. Yeah, it's just a little. It's not much. It's just a few values up there. Page 123.
When something's going vertical or horizontal, then I use a minor head loss chart.
If you're going through a fitting,
Okay.
you know, you can. This is a real small chart. You can find values for all sorts of different fittings. Right. Oh, we're good with that? Because there's one other thing I want to look at here. All right. And the last thing to look at here, another little pump thing. We got a few minutes. Another calculation you can do with pumps. It's called NPSH. Okay. If we're good on that. And what NPSH is the energy that the water has in the volute, okay? And you need a certain amount of energy for the pipe to function properly when it's in the volute, or for the pump to function properly when the water's in the volute. Okay, so this is called net because it's a total, positive because it's a positive form of energy. It's on the suction side of the piping, and head for energy. So they just abbreviate that as NPSH. And what it is, it's telling you how much energy you've got in the water in feet when it's in the volute. And a pump needs a certain amount of energy to function properly. Now we got these two different conditions for pumps. We got static head and static lift. Static lift is what you worry about. This is what you calculate NPSH for. Normally speaking, if you got the reservoir, inlet reservoir above the pump, you're not going to have NPSH problems. The water's just flowing into the pump on its own. It's not a problem. Where you get problems is when you're lifting water out of a reservoir up to the pump. You may not have enough energy in the water by the time it hits the pump. It might start to even vaporize, and that causes something called cavitation in your pump, and that's trouble.
That's a cavitation bubble can break.
Yeah, I've seen impellers that came out of cavitating pumps. It's like they're all, like someone's been banging on them with a hammer or something. They're all spalled and chipped and everything.
Yeah.
You get a lot of forces built up because if the water vaporizes in the volute, when it moves to the high energy, the high pressure side of the piping, those vapor bubbles will just collapse, and it just starts.
Whatever surface is next to it will just impact it.
Yeah, right. If a pump's true cavitation state, it sounds like it's making popcorn in there. It just starts snapping and popping. It's really kind of an odd phenomenon.
Yeah. You ever seen some video like a mantis shrimp?
Oh.
There's these like
Oh no.
there's these things that have like these things that strike other crustaceans,
Mm-hmm.
and they move so fast that they create a cavitation bubble.
Oh really?
And they can crack people. Yeah.
Oh, okay. Yeah, I've seen that. There was a vendor that came around with a little van that had a display for cavitation. They had a pump with a clear plexiglass plate across the volute, and you could actually see it. It was pretty cool. So little kind of vapor bubbles started coming out off the impeller. It was pretty neat. Okay, so if we want to track how much energy we got in the volute, we're going to start with the water where it starts, and that's at the intake reservoir. So we're going to start right there, and the pressure or the energy the water has is the atmospheric pressure expressed in feet. Okay. So you're going to start with something on the order, depending, about 34 feet of energy. That's what you got. And I'm on page 141. Okay, now a number of things are going to take energy out of that water as it goes up to the pump. The first thing is the static lift. If you got 34 feet of atmospheric pressure pushing water up that piping, every foot up it goes, and every foot of elevation gain will take a foot out of your energy total. Okay, so that's the static lift. So you subtract that from your atmospheric pressure in feet. The other thing you got to look, or another thing you got to look at is the friction losses. That takes energy out of the water too, but you only look at the friction losses on the inlet piping side. Okay, not from both sides, only the where the water is flowing, and it's flowing through the inlet piping. So you subtract that off. And then the last thing is what happens in an impeller, in a volute, is the impeller spins and throws the water outward, and it creates a vacuum, but it's not a total vacuum, it's a partial vacuum. Okay, so the reason you can lift water with a pump is you get a vacuum in here, okay? So what you have in that volute is a vacuum, but it's not a complete vacuum. It's a partial vacuum, okay? So right in there, you've got just a partial vacuum. And how partial it is depends on the temperature. And so this is where we, I don't know if you remember, but we looked at vapor pressure just briefly a long time ago. This is where we care about this, because the higher the temperature goes, the more that water evaporates and the more back pressure it causes. And this is called vapor pressure, and it works against your ability to lift water into a pump. And that's on page 58. So what you'll see is you get, a couple feet of vapor pressure when it gets hot out there. And that'll work against your pumping.
Is that when vapor walk?
It could, yeah. Yeah, if you get enough pressure pushing back where you can't lift the water up. So if you're having these kinds of problems in a pump, the common things you look at to fix it are, you look at this equation. There's not much you can do about vapor pressure. It's just a function of heat, of temperature, I guess I should say. That's on page 58. But you can influence the static lift. So if possible, lower the pump down. Get it closer to the reservoir. The other thing you can look at is the fittings on the inlet piping. You want to minimize those. You don't want a bunch of bends. You don't want a bunch of valves and stuff like that on the inlet side, because it increases the head loss. So those are the two things that you can do to decrease the energy being robbed from the water as it goes up, and to increase your NPSH, which is what you want. You want a high NPSH.
What page is this again?
So on page 141.
141.
So if we got this pumping set up right here on page 142, we could find the NPSH. And what you're doing, you're just finding those four things, okay? So for this particular pump, the atmospheric pressure, I think, it'd be 34 feet. That's the standard atmospheric pressure. Okay. Okay. Then we can look at the vapor pressure. What's the temperature on this one? 70 degrees. So go to page 58 and look at 70 degrees. That's not a whole lot, I don't think. Yeah, it's on page 58. See, that's going to push back on the water as it's trying to come up the pipe. Okay, the static lift. What do we got for the static lift on the suction side? Yeah, 7 feet. because the pump is up there at 501 and the reservoir is at 494. So the first three things are typically pretty easy to find. It's the last one that's a little bit more challenging. Okay, and that's the head loss. So we got to find the head loss for this. So to get the head loss, we look at how long the piping is. You're given that. I think it's 12 feet of pipe, if I'm not mistaken. Okay. And then we got to do the whole deal on the fittings, okay? So we've got a standard elbow. So you can look up L over D for that. I think it's 64. So we've got these fittings we got to deal with, and maybe I'll kind of redo this just a little bit. So the standard L has an L over D value of 64. And what size pipe do we got? Is it 8 inch? Okay, so 8-inch pipe is 0.667 feet. So that will get you an L equivalent there of 42.7 feet. We've also got an extended outlet. As the water leaves that reservoir, it goes into that pipe that sticks into the reservoir. So it's not flush, it's extended. L over D is 28 times the pipe diameter of 0.667 feet. And that will get you 18.7. So for the fittings, we got what, 61.4 feet? Okay. So we just look at the length of the pipe, which is 12 feet. We look at the fittings. So our L total is 12 plus 61.4. And that's 73.4 feet. Okay, and then we just look up the head loss for that piping. And that's 4.85 feet, which is off the charts on page 108. Multiply that by 0.734 foot lengths. And what you get for that is 3.56, 3.59, okay, 3.59. And that's feet, okay. So what that means is you started with 34 feet. You got 0.8 feet of vapor pressure pushing back from the volute. You got to lift the water 7 feet, and you've got 3.59 feet of head loss. So that what's left over is the energy the water has in the volute. And that'll tell you how much energy you've got. You can look at your pump curve and see if that's enough for the pump to function effectively. Okay. So that's how that works. Okay, so that's 34 minus 0.8 minus 7 and minus 3.59. So what you end up with is your NPSH is equal to 22.61. And then you look at your pump curve and see if that's good enough, if the pump will function properly, if the water has that much energy. This isn't as important as TDH, but it is something that you look at sometimes when you're lifting water. Doing all right with that? And, you know, I've seen pumps that are made to lift water. They'll have a little NPSH, required NPSH line on them, on the pump curves. That'll tell you what you need for different flow rates. So you'd calc this number and compare it to what you need, make sure you've got enough. Okay. You doing all right with that? We got any questions on that, Ben? So that one, you got the formula again on your formula sheet. You know, I just